So now in this video, we're going to be looking at switching a load that may exceed or push the limits of a bipolar junction transistor that's in the TO92 package. So this one is the TO220 package. They have a tab that helps dissipate heat. They can easily switch more current. But also that tab, you can attach a heat sink, which I already have there. That helps even more. But I don't even think we need it, but it doesn't hurt, and they aren't that expensive. So in any case, it's an NPN bipolar junction transistor still. It's wired as a switch. So when I give it a signal by closing the mechanical switch, of course this load I probably could just switch with the mechanical switch. But usually you would use something else for the signal. This is just for demonstration. But that turns the transistor on, and thus we have the load that's turned on. Now, each one of these is going, when we have 5 volts, which we do here, each one of these is going to pass at least 200 milliamps of current each. So a total of 400. And so we should probably, guess that we should wire the circuit to be able to handle 500 milliamps at least. And the 2N2222 can do that, but that's still kind of high. I would probably go with a higher wattage transistor. So now what I showed you earlier with everything may have been all some people needed, but here we'll zoom in for those that want more details on this. So this is a symbol that I came up with for these LED modules. That's what I call them. All they are is there's an LED on there, a resistor on there. They wire it together. I had to solder the 2 terminals on there. I had an old iron that was rusted, and so it didn't do terribly good. But in any case, good enough for now. And there's a heat sink on there that helps dissipate the heat. It gets really hot, so do not pick that up if this has been on for a while. It should cool off, fairly quick once you cut power, but wait a little while. So in any case, they're parallel. They are together. One of them is pushing the absolute limits of a 2N3904 NPN bipolar junction transistor. They can only switch about 200 milliamps of current. That's what you can really expect across one of these when you got 5 volts. They set the current based on the resistance that's already on there. You put the voltage across it. But if it's 5 volts, you can expect somewhere around 200 milliamps of current. The absolute limit for the 2N3904. 2N3906 can switch 600 milliamps of current. So both of these together in parallel, you're going to get about 400 milliamps of current. So that may be okay. But I still think, that's getting, 2/3 of the way to the absolute maximum current. And I usually try to stay halfway or below as much as possible. So we're going to grab this higher wattage transistor. Now again, it's not in the TO92 package, which is this right here, the most common package you see on DIY videos. So technically the most common package might be surface mount, for on boards and stuff. But if you're building circuits yourself, you're probably going to use these through-hole components that you can plug into a breadboard. So we got the TO220 package right there, and this is the metal tab. There's more metal on the back, so the side where the plastic sticks out would be the front. And you always got to check the data sheet for the pin layout when you're using a component you're not used to using. Even if you're used to using, check it out, because sometimes I misremember what the exact pin layouts are. But for this particular package, TIP31C, I just got it from a kit. I'll try to remember to show the kit later. Base to the left, collector in the middle, and emitter on the right. So we will look at that on the board right here. It's pretty straightforward. You can see the switches at the bottom. Usually I work positive coming down, but they would kind of hide the switch. So I put the switch in front here. Positive working our way up in this case right there. And so you can see the 3 pins there. This is the heat sink I got. These are not terribly expensive. I recommend getting them, especially if you get a lot of TO220 package integrated circuits right there. So one thing to point out, left pin is the base, and then let me check the sheet, make sure. Middle pin's collector, right pin is emitter. If we turn it this way, now the base is on top right there. And this heatsink kit came with a little heat pad that I connected between these two. Put that on there, and then you just screw, I think through the front there, that down. So in any case, The resistor, it's kind of hard to see, is going up above the jumpers there. One row above the yellow one. And we will, I'll move it off to the left. But yeah, you can see it lines up right there. Hopefully, let's double check that it works. There we go. And, you know, I'm looking through the camera. It's a little hard to see what's going on. So resistor is going up. That gives us our signal to the base. So it's relatively low current, but this is a relatively low value resistor, which will give us a higher current than generally we use for transistors. And I'm not sure the gain of this particular transistor, but generally when you get to higher wattage transistors, unless they're specially made, their gain is probably not as good. So gain means, we'll just use milliamps for make this easy. If you're getting 1 milliamp of current flowing base to emitter, then it might be able to switch. If it's a gain of 200 milliamps of current, and so on right there. So we're getting a lot more current going through the base to emitter because we have a higher current load, but also when you have higher current loads, these larger transistors, the gain also isn't always as high. So maybe it's a gain of like 50, you know, for 1 milliamp of current, it will switch 50 milliamps and so on. So in this case, if that were the case, we'd have to get at least 10, you know, milliamps of current to switch 500 milliamps. So hopefully that makes sense. That's basic transistor stuff. But that's why I have a relatively low value resistor. You know, I could do a lot more testing, try to figure out the gain on top of looking at the data sheet, but not really required. Main thing, get, you know, a fairly low value resistor there and switch it. See if you're getting the full current that the load will provide. And if you do, if you want to, you could use a higher value resistor and see if it still will switch that full current. If it doesn't, you know, drop back down. So you could do that. I don't think I did that there. I think I just kind of grabbed a resistor that should work fairly certainly. So probably could go higher. But yeah, we will not ramble on about that long enough. So yeah, that pretty much covers this. Again, you do not use like a physical switch to switch something like that. You could just put, you know, even this push button switch right in series with it. That's not the main point. You may have other circuitry that can provide, you know, 10, 20 milliamps of current, but that's it. It could switch like that much. So in that case, you would switch the transistor on and off, and then the transistor would be able to switch the load. So be aware of that. You might have like Arduino. I don't think you would switch this transistor directly. I could be wrong. I don't do a lot with Arduino, and that was a long time ago. But if you're using like an Arduino, you don't want to be like switching like even like light loads, like LEDs. Really, you know, they can provide the power, but it'd be better to switch transistors. That way the power going through the LEDs comes from the power supply, and all the output of the Arduino or whatever is doing is switching the transistor, which requires a lot less current. That will put a lot less stress on the Arduino. Of course, there's always exceptions. You got to look for the limitations of them and whatever, but that's generally why transistors are used. People often ask, why are you using a transistor when you can switch it with the switch directly? That's because this is just a demonstration circuit. If I was switching it with more complex circuitry, I'd have to explain all that other circuitry and stuff. You know, people would be like, why don't you break this down into simpler topics? So in any case, that was enough of a rant. I really kind of covered everything anyways. But yeah, if you look at the data sheet, I did this a long time ago, but I assume this is correct. The maximum current you can switch is 3 amps right there. The maximum current you can get through the base is 1 amp. And, you know, that may be more significant to know with this particular transistor, the base current that it can handle, than an NPN bipolar junction transistor, because I'm pretty sure the gain is a fair amount lower right there. So as I said before, this probably depends on more base to emitter current than a TO92 package transistor probably does. Again, you always have to consult the data sheet. So again, TIP31C. So to wrap this up, this is the box that I got this out of. I bought a bunch of different semiconductors. After you get the basic components, I recommend getting kits that have as wide of a range of semiconductors as possible. You know, get one kit and then try to find another kit that has a lot of semiconductors that you still don't have or whatever, and so on until you get all the ones that you want. But in any case, like if you just want this one, I still recommend getting a kit where there's a wide assortment, unless you absolutely need a whole lot of them, just so you have all the other ones. So this is the NPN transistor. This is the PNP version. And so unless they got this wrong, every once in a while I think I find them wrong. You know, pin layout's the same, but the chemistry is opposite, so current flows in opposite directions. So that's why you see a negative current right there and a negative voltage. In relationship to this one, the voltages and the currents are in opposite directions right there. And so we also have, so that's the 31C, this is 41C for this particular kit right there. And yeah, it looks like that can handle a lot higher current. So I'm guessing these conduct better when they're on for whatever reason. That's what I'm guessing. And I'm guessing that they just can't be switched as fast. You know, they can be switched fast, I'm sure, but probably not as fast as this. So if you need really rapid switching, I'm guessing those would be better. That's kind of the way it goes. They usually kind of compromise how much current they can handle versus how fast they switch and whatnot. So yeah, you can see right there, power transistor. So I think that's bipolar. There's also a MOSFET. I think it's just an N channel. Yeah, for some reason, yeah, they gave me a couple N channel. It's kind of hard to find a P channel MOSFETs. There you can see that's Darlington pair right there. And then these, yeah, it looks like just kind of a lower wattage and a lower voltage able component. So yeah, maybe you do that, you know, with the heatsink, it would be just as big. But yeah, maybe you would use this for like when the NPN won't quite cut it, so you're going to need a little bit more, but don't really want to add a heatsink. You know, that's kind of or a very small heatsink, something like that. But yeah, in any case, this was just kind of extra stuff. I got it from this kit. There's a bunch of other ones right there. This does not have the 2N3904 and the 2N2222 though. So I recommend getting those from different transistor kits. And often they just come with basic component kits. Enough of them so that you might not even need to buy anymore. But yeah, that's it. Thanks for watching. Make sure you check out one of the other videos I posted on the screen and check out the links down below. They all help out a lot. I'll see you in the next video.